Hello everyone, the title of our paper is Adaptive Traffic Light Congestion Control with RSU Assistant in VANET, prepared by Dr. Saad Talib and Randa Mehdi. These are the contents of the paper. Now the abstract. A vehicular ad hoc network VANET is a type of wireless network that allows communication among moving vehicles with the assistance of roadside units. Congestion in VANET refers to the situation where there are too many vehicles on certain part of a road, causing a bottleneck in the flow of traffic. This congestion can lead to delays, increased travel time, and reduce overall network performance. In addition, congestion in VANET can also lead to a higher probability of collisions and accidents, as vehicles may be unable to communicate effectively with each other or with the infrastructure. Therefore, managing congestion is a critical issue in the design and operation of VANETs to improve the intelligent transport system in an urban area. In this paper, an adaptive traffic light signal using the assistance of roadside units is proposed. A technology has been built depends on density of vehicles in each of segments of the routes connected to the traffic lights at the intersections. A prediction is accepted to calculate the congestion on its spaces and open the road automatically when congestion occurs on any direction. The results show that the proposed model makes a stable movement of vehicles to cross the intersections in urban environments. Now the introduction. Intelligent Transport System (ITS) is a technology-based solution that integrates advanced communication and information technologies to improve transportation efficiency, safety, and sustainability in urban environments. ITS uses sensors, cameras, communication networks, and algorithms to collect and analyze data about the traffic flow, vehicles movement, and weather conditions. It helps reduce congestion, improve mobility, and enhance safety by providing real-time information to drivers and traffic managers. This communication can help improve safety, reduce traffic congestion, and enhance the overall efficiency to the transportation system. The VANETs are a key enabler of some ITS applications such as intersection collision avoidance, intelligent parking, and emergency vehicles priority. However, VANETs are exposed to several challenges and problems that can affect their performance and reliability, such as connectivity and communication, security and privacy, scalability and deployment, equality of servers, and energy efficiency. Urban areas are usually the centers of economic and cultural activity, with higher levels of economic activity, cultural diversity, and social inequality compared to rural areas. The physical features of urban areas may include tall buildings, transportation infrastructure such as highways, bridges, and public transit system, public spaces such as parks and places, and other mentions such as shopping centers, restaurants, and entertainment venues. In this paper, a model is proposed and developed to facilitate the vehicle's traffic flow and respond to serve the emergency cases by minimizing their waiting time in traffic light and intersections. The related work. At the 2018 proposed a pipeline model of adaptive traffic light scheduling in urban areas based on vehicle to infrastructure V2I communication, and at 2020 proposed a system developed and implementation of a smart traffic lights control signal system for improving traffic flow, a smart city environment that at 2021 proposed at adaptive traffic signal optimization system that utilize deep reinforcement learning to optimizing traffic signal timing in real time. Finally, at 2022 proposed a system for implementing virtual traffic lights using roadside units and wireless communication in vehicular environment. The density of the car's VANET. Let us denote the density of cars in the nearby road by the symbol ρ, the number of cars by the symbol N, and the length of the nearby road by L. The mathematical equation for calculating the density of cars in the nearby road can be expressed as follows: ρ equal N divided by L. This equation simply divides the number of cars on the near roads of the length road to the car of density. Let L equal 1 kilometer, then the equation of density represents ρ equal N per 1 kilometer. Minimum number of vehicles in a specific road segment length, which results in a congestion case, can be calculated in a developed equation. N equal distance divided by the average of vehicle length plus the safety distance between two cars multiplying by the number of length. The proposed approach. To implement the proposed approach, network simulation is used a bold virtual urban map consisting of roads with an intersection. The unit is distributed according to its coverage at distance of 2 km between one unit and the other, so that there is communication between them in what is known as a connection. Controlling the occurrence of congestion in the cooperation with the roadside units, where this is done by determining a specific threshold for the number of cars within the specified range, which is B, will be measure of comparison with the traffic flow. Criticize the term threshold is the maximum number of the traffic flow that can be accommodated with causing congestion. This threshold can be set based on factors such as road capacity, vehicle density, and travel speed. When the traffic flow can be expressed in terms of vehicles per hour or vehicles per lane per hour, the traffic flow can be measured using traffic sensor or manual traffic counts. Once you have measured the traffic flow, we can compare it to the threshold we have already defined. If the traffic flow exceeds the threshold, then congestion is likely to occur. Then the degree of the congestion can be determined by how much the traffic flow exceeds the threshold. For example, if the traffic flow is only slightly above the threshold, then the congestion may be mild, while much higher flow would indicate severe congestion. Before we compare traffic flow with the threshold value, we must note that the range of the RSU is circular, meaning that it can include vehicles in the other direction of the road, not just the desired road. That is why the cars must be divided according to the direction you are going in order to correctly calculate the traffic flow for the route. Based on what was mentioned, we determine the degrees of congestion according to the number of vehicles in the range of the roadside unit as follows. If the number of vehicles greater or equal the threshold value within the range of RSU will be congestion. Else, if the number of vehicles smaller than the threshold value within the range of RSU will be no congestion. Now when have determined the congestion, can take the action of elevate it. The simplest of these procedure is to take adaptive traffic light with the traffic where the roadside unit sends a signal to increase the time or for the passage of vehicles within the busy road to reduce the congestion and distribute it to the rest of the roads. In figure 3, a flowchart shows the steps of making the proposed model, while algorithm 1 explains the working mechanism to implement this model. This is the result for run the simulation. The threshold in simulation equal 10, and the result in congestion in north or in east, the traffic open. the analysis of results. This is the result from the simulation. Finally, the conclusion. In this paper, an adaptive traffic control model was proposed. This model, when implemented, will overcome the congestion problem caused by the traditional traffic system. By calculating the traffic density through the number of vehicles on the road, threshold was given to estimate the occurrence of congestion based on several factors, including RSU coverage and the number of cars within this coverage. A model was built through an algorithm that works on estimating the occurrence of congestion through the threshold and working on opening the traffic light for the busy road and closing the traffic light for other roads. And in the event that the roads are not exposed to congestion, the traffic lights return to their additional work. The result obtained from the simulation, when analyzed, showed that the proposed model regulates the traffic of vehicles and reduces the congestion, which makes the movement of vehicles in urban environment more stable. These the references for the papers. Thanks for you.